Hello. So I will discuss some highlights in perspective in network calculus, just to describe some of the work I've done when I was at Huawei during the 5 past years, because I'm back a few months ago at ENS. So we look at the problem of evaluating the worst case performances or end-to-end delays in network. The objective is to compute time performances in a critical network when you want to guarantee some delays. So you can find some applications in avionics or vehicular networks, industrial or optical networks. For example, here you have the example of an industrial network. For example, you want to control the delays of a robot arm in the street chain. And you have different types of traffic. So, for example, control traffic or sensors, when the end delay requirement might be on the scale of the milliseconds. And you also have other types of traffic, like video or images, where the requirements in terms of delay might be 10 milliseconds. You can also have different types of connection, like wired network or wireless connections. And network calculus is a theory that aims at computing worst-case performances in networks. So what is it more precisely? So you are given a network with different nodes that are the switches that will serve the data. And here, the paths of the data are represented by the red rows and paths in the network. And network calculus is doing a few things. First, it will model the data that arrive into the network. So, for example, it will be given by an arrival curve that will model the amount of data that can arrive during each interval of time. You want to bound this. And this is either given by learn with the data or computed with prior knowledge about the characterization of the data. The second thing we want to model is how data are served at each point of the network. So this is a model by the service curve. And this service curve depends both of the scheduling policy, so in which order the data are served in the network, in the service element, and of the bandwidth at which speed data is served. And once we have computed this for every class of traffic at every point of the network, we can combine the arrival curves and the service curves to compute the performance bounds. Usually, we will compute worst-case upper bound, for example, of the end-to-end delay, but it can be also in a probabilistic setting, which is something I will not deal in this talk. And the second thing is when we know how to compute performances, we have good analysis tool. We can do some optimization on design. For example, how to optimize the parameter of the schedulers, how to do some routing to find the best path for the data, or do some admission control. And now, when we want to analyze a network, so as I said previously, we might have different classes of networks that have different requirements. So we usually have a multi-class network. So inside each class, in fact, the data will be served in their order of arrival. So we will have a FIFO network. The first step in analyzing this network is to model the scheduling policy for each router. And then we can obtain one FIFO network per traffic class. And when we have done this step, we can have some analysis tool for the end-to-end delays of the FIFO network that we will compute for each of these networks. So the first result, for example, on the bandwidth sharing policy. So one example is DRR for deficit round robin, where data are served in rounds. And maybe you can see that as an alternation of periods of time when one class of data is not served, and periods of time when so this is round for the other classes, and rounds for your classes when the data are served at the maximal rate. And then there is a first result by Boyer and Stea to compute some linear approximation of this DRR policy. And but you can do better. And because this is done when you compute the service this way, you don't take into account the traffic, the arrival curves of the other classes of traffic. So in this work, we compute the service curve for each class of traffic that depends on the guarantee for one group of classes and on the parameters of the scheduling policy. And there is one parameter here that is due to the packetization because data are not served in a fluid manner, but by packets. And here you can improve the service curve that way by having slopes here with a higher rate. So, and you can compute better delays. And once you have done this step, you can define one FIFO network by traffic class, and then you can analyze the FIFO network. There are different ways to analyze the FIFO network. The most classical ones are the modular methods, when you compute one delay for each server, and then you sum all the delays for all the servers on the path. But when you do this, you do a by server analysis. And this model is quite general and has a small complexity. You can compute the performances quite fast, but usually they are not very precise. And what we did was we defined we adopt a different point of view when we want to model everything that happened globally in the system to compute directly the end-to-end delay. So here we model this with a linear program where the variables are sometimes at which you need to know the value of your functions and the value of your functions. And the linear constraints are given by the network calculus constraints, the arrival curves and the service curves. And when you do this, you can compute the exact end-to-end delays. But the drawback is that this is a very expensive algorithm because you use an exponential size linear program that also has some Boolean variables, so which is make it doubly exponential to solve. And what we define here is a good trade-off between the complexity and the precision of the bounds by simplifying the linear program into a polynomial size linear program to compute the performance bounds. So if you look at the problem of the stability on the simplest network that is a ring, with the modular analysis, the stability is always less than 0.33, meaning that if your arrival rate at each server is more than 73% of the service rate, then you will obtain an infinite bound. But if you use the linear programming method, then the stability is 1, criteria is 1, meaning that if every server is locally stable, then you can compute a finite bound. And when we want to apply this to a multi-class network of industrial size, if the network is heavily loaded, you might not obtain a finite delay with the modular methods, but with our methods, you can obtain finite delay bounds. And when the utilization is like 40%, you don't have a so strong utilization of the network, then you can compute finite bound in every cases. But here we could divide by 3 the number of the delay bounds for each flow. Okay, but one thing I want to say about computing the computation time. Usually, many authors say that the linear programming methods are really too expensive when you want to compute delay bounds in large networks. And they also have another method, which is LUDB, for least upper delay bound. That is a mix between optimization techniques and modularity. And some authors want to don't really compare to the linear programming methods. So what I wanted to do is try to compare with these, because they give a set of 31 network. And then I wanted to compare with the linear programming method. And this is what we obtain. So here we see that the first shows the delay bound. So we see that the LUDB method is on average 25% higher than the linear programming method. And the good news is that we could compute actually the bound in a reasonable time. And when we compare the computation time, we notice that our computation time are either similar to the optimization techniques of the concurrent work, and it can be a little less. So here, in fact, we can compute better delays in a little less time or equivalent time. So the trick here is something I couldn't really do at Huawei because I used Cplex to solve the linear program, which is something we couldn't do because it's an American software and proprietary software. So instead, the first implementation, I used LPSOL, which is a little less efficient, but using Cplex now gives better results. And finally, the question is it computing network calculus an endless battle to who is getting the smallest delay? Because it's what is happening actually. And one thing that is never done is, can we compare to the simulation? Because usually when you have a queuing system and you want to improve the analysis of a queuing system that is modeling probabilistic performances, you always compare to simulation, and it's very easy to do. But here, what we want to do is computing the worst case delay. So, and sometimes for people from industry, they will say, oh, you can compute bounds, but they are very different from what we obtain from simulation. For example, in the first example that I had in Huawei, they said, we have a network that was a tree topology of about 15 nodes. And they say, but our delays are really different from what we obtain in the simulation with the analysis. So the first thing I did is I used my own method with linear programming. So for the three classes that are not so critical, the pessimism was 20 to 30%, which in that case was quite okay because it's reasonable. But for the more critical class of traffic, we obtain a factor 5, so which means that our bounds are really not good. So question is that our analysis is not good, or is it the simulation that is not good? And what we could do, we could show that the simulation should be at least 100 microseconds. Because what they did in the simulations, they say, we make all the traffic arrive at once, and this is our way to simulate the worst case. But you can always do better. You can try to think what is the worst case synchronization and how to do it. So maybe what I want to do now is to do some worst case simulation, see what is the worst case to synchronize data, because these are things we will never be able to obtain with Markovian simulation, for example. So these are first results. So here I tested on tandem networks that are a line network of small size, because I wanted to be able to compute the delay bound with my exponential linear programming techniques. So when I compare, so we can use some, either use the solution from PLP, because they give some information about what is the worst case trajectory. So how I can make my flow in order to try to simulate a worst case delay. And so when I do the simulation, then I have an actual simulation that will give a lower bound on the delay. And I can compare with PLP or ELP. Here I compute with ELP. And what you can see is the pessimism on randomly generated network is almost less than 5% for more than half of the trajectories. So you can have a pessimism of more than 40% for kind of exceptional cases, like it's 1 over 1,000 case, but usually you are able to compute some approach, in fact, some worst cases. So, okay, in conclusion, so we presented some improvement in network calculus. There is still room for improvement, but I think that what is also important is to be able to generate worst case trajectories to either to show the efficiency of our approach, or also give to industrial people ways to say, but your bound is might be more than this if you do things smartly. And there are also new applications that have been developed in recent years or to be developed, like spatial network calculus or quantic network calculus, if ever Remy make me understand what is quantum computing. And I'm open to collaboration. Okay, thank you.
Thank you. It's very interesting. I had a question about the last part, and I think it was interesting that you were pointing out that the solution of the LPS was actually giving you hints at that. So when I think, and one of the challenges that I've encountered in dealing with network calculus is that, so the upper bounds, the looseness of, even forgetting about the fact that the bounds themselves are loose, right? There are sort of, in the network calculus framework, there are sort of two things that introduce deviation from what you get from simulation. And that's inherent in this worst case guarantee sort of approach, right? One of them is that the traffic envelope is an upper bound for the temporal behavior of the sources, right? And the second one is sort of a spatial upper bound, right? If I have two flows, then I can figure out what is the worst case when I combine them, or maybe I shift them a little bit. But if I have 1 million flows, what are the odds that they all line up in that worst case? So the gap between the probabilistic result and the worst case guarantee, which is what network calculus, right? And so I'm actually interested in your perspective on that latter part, right? So if I have a network with 1 million flow, does it actually make sense to attempt the network calculus type of approach?
Okay, thank you. In fact, we have some result on this precise problem because we look with Jean-Yves Leboutek and Owen Tabatabe. We look at the problem of, we have periodic flows and they have random phases. And then we have result on if you have random phases, you can really improve the backlog bound when you aggregate all of them. And you can really reduce the burst. And then when you do some worst case analysis, then you, instead of computing a deterministic bound, which is always the sum of all the arrival curves, then you have a probabilistic bound. And if your bound is respected with some probability, then you know that your bounds will always be respected on time, because we use also perfect periodic flows.
Thanks.
Yeah, so I think, thank you for the, I think to Rock's session, the thing, if you remain purely deterministic, yes, you must always take the worst of the worst cases. Everyone, collude to send exactly the traffic up to their traffic envelope, and there is nothing you can do to fight against that, even if it is a very unlikely situation. But essentially, you put a probabilistic model on how unlikely it is. If you want to take the case where this can occur, even if it has a very, very small probability, you would get these bounds that scale with everyone else. Now, in much easier case than the model of the ring that you have, it's possible to arrive to tight bounds. So essentially, you know that there is a deterministic pattern that goes for that. And I understand that what you want to arrive at the end is basically to come with what is the arrival patterns, essentially, that fulfills the arrival curve and so the constraint that essentially is difficult to get by chance, by simulation, but essentially that would guide a little bit the simulation on what to test for, you know, the black swan case. I mean, essentially where you have things go very wrong, so that it helps. And by just a Markovian simulation, the probability is so small that you don't get it easily. And so that's, I guess that's the output, because in these cases where you have multiplexing, it's very difficult to get tight bonds, right? It's probably beyond reach.
Show the tightness like with this exponential linear
Yeah.
program on Boolean variables. And also in the case of black multiplexing, because we know, in that case, we know that what is the worst, let's say, in, entre guillemets, worst scheduling policy, which is like the shortest to deadline first.
Yeah.
Then we know. But otherwise, yeah, we have to apply some heuristics and guess a little what is. And this is very preliminary because.
But I think it's useful in terms, because this discovering what is the dangerous case is difficult to do by pure simulation. And so that can be an aspect where essentially it's useful to guide simulations as to test, oh, these are the situations you should test your network. And so that I think is very valid output of the research, even if it is not the bounds in themselves, it's what is the cases to simulate that are useful. And the second part is exactly, so I was giving the periodic flows with independent phases and so on, because there are very few results on the stochastic part which are convincing, right? In the sense that you lose the tightness usually as soon as you do, you relax a little bit the deterministic one, except that work, which seems to be exactly, so you keep the determinism per flow, I would say, you just have one random aspect, and essentially it gives much tighter bound. It is very convincing. And also, you know exactly that if you lose, you know, the independent phases, then it's no longer valid. So essentially, it's clear the context in which you provide these guarantees. And so that I think it's a good, promising avenue for network calculus, because I think it indicates essentially that finding bounds in the stochastic regime that are meaningful is really a hard quest to get.